So today we'll discuss about the distributions. So law of large numbers we'll discuss later, and then generating functions of probability generating function and all. Okay. So weak law of large numbers and strong law of large numbers will be discussed at the time when it will be required before discussing about the class. Okay. So there now today we'll discuss theoretical discrete distributions. There are so many distributions are there in theoretical discrete distributions. So what does that mean by distribution then? Because first we're going to discuss about the distribution every time. So what is the mean by distribution? That how your probability has been distributed to the each and every random variable. So that makes you sense that whether it will be follow which type of distribution like that. So depending upon that, so it will be mentioned that so Bernoulli, binomial, Poisson, negative binomial, geometry, hypergeometry, like that. These are all these distributions are comes under discrete distributions. So once we discuss about the discrete, then we go with the continuous one. So first distribution will start with Bernoulli. Bernoulli distribution. So Bernoulli distribution. So just it takes only two values of the distribution of the a random experiment. So let it is a random variable x. You can take a random variable x. Takes two values that is 0 and 1 with probabilities. Okay, x takes only 0 and 1 with probabilities p and q. Okay, so what does it mean, p and q? If probability of x is equal to 1, then you can consider as a success, and probability of x is equal to 0, you can consider as a failure. Okay, so the distribution is, if you make only this success and failure for a random experiment, simple, there is no other alternative of this distribution of a random variable, then such type of situation we can say it is a Bernoulli, because you have only two values of the distribution. So based on that, you can find out the moments of this distribution. Just it doesn't have any proper mass function of this Bernoulli distribution. Simple, it is P and Q, and then so that let it be at x is equal to 1, you can get the success, and x is equal to 2, you can get the failure. So that your success plus failure plus success, or maybe success plus failure, is equal to 1. That is total probability. Okay. So first we can go with the moments of the Bernoulli distribution. Moments of the Bernoulli distribution. So what type of moments we can solve this Bernoulli distribution? So first, in general, we can start with the rth moment. That is, we know that mu r dash is equal to expectation of x power r. Generally, as discrete distribution, we have expectation of x power r. How we can write? Summation over x power r of your mass function. So here I can write, because summation ranging from 0 to 1 and 0 and 1, okay, of your probabilities. That's, you can say it is a 0 power r into q plus 1 power r into p. Because at 0 your mass function is q, at 1 your mass function is p. So that it is your p. So mu1 dash is expectation of x, that is p, and as well as mu2 dash, that is expectation of x square, that is P again. Okay. So variance of X, how can find out variance of X? Expectation of X square minus expectation of X whole square. So that is P minus P square. That's simple. I can say P into 1 minus P. This implies P into Q. So here you can write Q is equal to 1 minus P or P is equal to 1 minus P. Okay. So here we should discuss one remark in that. That is, what does that mean? What is the remark? Is it degenerate random variable? Degenerate random variable. So degenerate random variable, sometimes a particular entire distribution, the entire probability will be concentrated on what only particular one place, which means maybe you can take probability of X is equal to C is equal to 1 and 0 otherwise, or you can say 1 0 otherwise. X is equal to 1, X is equal to C, it is 1, otherwise it's 0. Which you can write it like this: probability of X is equal to C is equal to 1, so that automatically your variance of X is equal to 0 here. So such type of situation and such type of random variable, you can say it is a degenerate random variable. Actually, the entire mass and the whole mass is concentrated on a single point. Whole mass concentrated on a single point. Even in Bernoulli distribution, mass has concentrated on 2 points. At X is equal to 1 and X is equal to 0. At X is equal to 1, your probability will be something, and X is equal to 0, your probability will be something. Okay. So it is not a degenerate. Degenerate means success and failure, your concentrated entire whole mass will be concentrated on a single point. Then you can say that is degenerate random variable. So such type of distribution, even moment generating function of the such type of distribution also, how we can write expectation of e power tx, that e power ct probability of X is equal to C. So simple it is e power Ct. Okay. So it's like, you know, single, if it is a degenerate random variable, how you can find just variance doesn't exist anywhere there. Only your mean will be exist. And coming to the second distribution, binomial. Binomial distribution. Here, let a random experiment, or we can say Bernoulli experiment. What does it mean by Bernoulli experiment? Bernoulli experiment having success and failure. Success and failure. The Bernoulli experiment repeatedly, means that n number of times it has been repeated. Okay, n number of times had been repeated, or maybe n times your Bernoulli trials has been repeated. Here n being a finite, you can say. Okay, n number of trials, you can say. Number of trials. And you can say it is a P is a success for each and every trial. So here, every experiment, your probability will be constant. Okay, probability of a success will be constant for each and every trial. So now, the Bernoulli binomial distribution exists. The Bernoulli distribution exists if there are the probability of X successes, means that the probability of X successes from if let it be, there are X successes, definitely N minus X failures will be there. We'll go to see, there are total N number of trials. Let it be N successes are there, definitely N minus X failures will be there. Okay, that is means which will be like that, probability of success, failure, success, and so on, success, failure, success, like that. Because we know that every trail is a independent. So this can be written as P of S, P of S, P of S, P of F, and so on, P of S, P of F, and P of S. So this can be, success will be P, Q, and so on, P, Q, and P. Okay. So here, as per this information, okay, as per this information, so N minus X failures and X successes. So as per this information, this will be successes are X successes and N minus X failures. Now, you have X successes and definitely N minus X failures out of N trials, right? N trials. So now, in how many ways you can, how many ways you can draw your successes? Okay. So N, C, X ways. That's why your mass function of this binomial distribution, that is probability of X is equal to X, will be NCX, P power X, Q power N minus X. Okay. So this can be written as, you can expand this one. You want to expand this one, Q power N, NC1. First trail is Q power N. Second is NC1, Q power N minus 1 into P. Third is NC2, Q power N minus 2 P square. And fourth one is, and so on. Final one is P power N. All are the successive terms of the binomial expansion. Can I write a binomial expansion? This one is Q plus P whole power N. Got it? Q plus P whole power N. So here the remark is, or maybe because it's we can say it is a probability mass function. X is equal to 0, 1, 2, and so on, N, because N being a finite, and 0 otherwise. So now, if summation X is equal to 0 to N, P of X, what you can get? Summation X is equal to 0 to N, NCX, P power X, Q power N minus X. Definitely it will be your Q plus P whole power N. That is 1. Total probability is equal to 1. If there will be another remark is there. Let us suppose that N trials constitute an experiment. If the experiment is repeated capital N times, if their experiment is repeated capital N times, okay, then the frequency function, not the distribution, frequency function. That is f of x is equal to capital N into p of x. This is your frequency function. Or you can write capital N into ncx p power x q power n minus. Even this here also you can write capital N into q plus p whole power n. Okay. Actually, the physical conditions of this binomial distribution is each trail resulting in two mutually disjoint events. Mutually disjoint, I'm telling you. Mutually disjoint. In a random experiment. Mutually disjoint. This maybe you can say it is a success and this is your failure Q. Success P you can write and failure Q. And the number of trails are finite here. N being finite. Third one is trails are independent. Trails are independent. That's why you get p power x into q power n minus x. And success is constant for each and every trail. I can say it is constant. Constant for each and every trail. Now we can draw the moments of this, derive the moments of what is a binomial distribution. Moments. Either you can derive using what is a moment generating function or directly. So let me we can solve in the direct first. Then after that we can solve it is by using, we can derive by using moment generating function. Mu1 dash is expectation of x, that is summation x ranging from 1 to n, sorry 0 to n, x into p of x. So this will be summation x ranging from 0 to n, x into ncx p power x q power n minus x. X ranging from 0 to n, x into, can I write this one? N factorial upon x into x minus 1 factorial into n minus x factorial. P power x into q power n minus x. So xx will be cancelled. So this again I can write summation x ranging from 0 to n. So x ranging from 0 to n, we cannot say that it's x ranging from 0 to n here. Maybe I can say like, I can write like this. N into n minus 1 factorial upon x minus 1 factorial into n minus x factorial, so that x ranging from 1 to n, and this is p power x. I can write p into p power x minus 1 q power n minus x. So n and p are the constants, and summation x ranging from 1 to n, n minus 1 cx minus 1 p power x minus 1 q power n minus x. So this entire thing will be, it is, you can write q plus p whole power n minus 1. So this will be 0. Sorry, so this will be 1. So your expectation of x, that is mean of the binomial distribution, is n into p. So your n is number of trials and p is your success. Coming to the second movement, that is mu2 dash, expectation of x square. So if you know that expectation of x and expectation of x square, then only you can find out your variance, that is mu2. Then only you can find out your mu2. Hope you remember. So for this, summation x range from 0 to n, x square, ncx, p power x, q power n minus x. Okay. So can I write this one? Summation x range from 0 to n, x square can I write x into x minus 1 plus x. Then n into n minus 1 into n minus 2 factorial upon x into x minus 1 into x minus 2 factorial into n minus x factorial, p square into p power x minus 2 into q power n minus x. Okay. Or else this entire thing you can keep it in mind. This entire thing, maybe I can write into, this is same thing, ncx, p power x, q power n minus x. So in the next step I can write summation x range from 0 to n, x into x minus 1 into ncx, p power x, q power n minus x plus summation x range from 0 to n, x into ncx, p power x, q power n minus x. So now this entire thing you can apply here. What you can get? Summation x ranging from 2 to n into n minus 1 into p square, then n minus 2 c x minus 2, p power x minus 2, q power n minus x plus this entire thing, you know that np, that is x into p of x. It is your expectation of x. So from this I can write n into n minus 1 p square. This entire thing summation ranging from 2 to n, it will be q plus p, this one. And you can write the summation here, summation n ranging from 2 to n. So this entire thing will be q plus p, sorry, q plus p whole power n minus 2 plus np. Okay. So you know that expectation of x square and as well as expectation of x also. So definitely based on the known notation, that is mu2, that is mu2 dash minus mu1 dash whole square, or variance of x is equal to expectation of x square minus expectation of x whole square. So that is expectation of x square is your n into n minus 1 p square plus np minus np whole square. So I can write n square minus np square plus np minus, sorry, n square p square. It n square p square. So n square p square will be cancelled. You can get here n p square plus np. You can make np is a common. So it is sorry, minus np square, right? Minus np square. Then you can get 1 minus p. So that will be npq. So your variance of x is npq. So just to remember, mean of binomial distribution. Mean is np and variance is npq. Okay. So this you will remember in your mind that for binomial distribution, what is mean and what is the variance of a random variable. Binomial variate, if it is x is a binomial variate, what is mean and what is variance? Okay. So after that, you can find out the beta 1, beta 2, that is skewness and kurtosis and all. I think not necessary, but you can remember. You can remember that beta 1 is equal to mu3 square by mu2 cube. That you can find out your beta 1 in binomial distribution 1 minus 2p whole square by npq. And coming to the beta 2, that is mu4 by mu2 square, that you can get 3 plus 1 minus 6p cube upon npq. And gamma 1 is the square root of your beta 1, that is 1 minus 2p by under root npq. And gamma 2 is your beta 2 minus 3. That's simple, 1 minus 6pq by npq. So can we find out the moment generating function of binomial distribution here? MGF of binomial distribution. That is mx of t is equal to expectation of e power tx. That is what the moment generating function. So I can write summation x ranging from 0 to n e power tx ncx p power x q power n minus x. Can I write this one? Summation x ranging from 0 to n ncx p into e power t whole power x q power n minus x. Okay. See, if we write this entire thing with the summation, what we write? Q plus p whole power n. Right? Here, in the place of p, what you have? P into e power t. Can I write this one is q plus p into e power t whole power n of your, this is your moment generating function of the binomial distribution. Similar way, characteristics function of binomial distribution, simple. The characteristics function of binomial distribution is phi x of t is equal to expectation of e power itx. That is summation x ranging from 0 to n e power itx ncx p power x q power n minus x. This can be written as summation x ranging from 0 to n ncx p into e power it whole power x into q power n minus x. This can be written as q plus p into e power it whole power n of your, this is your characteristics function of binomial distribution. Okay, this is the characteristics function of binomial distribution. Now we are going to discuss about the Poisson distribution. Actually, Poisson distribution is a limiting case of binomial distribution. From from some conditions, we can say it is. We can write. So Poisson distribution is a limiting case of binomial distribution. What are the limits there? So that we can convert that, we can draw your Poisson distribution more probability mass function from the binomial distribution. Limiting case of binomial distribution. Under conditions are, first one is n number of trials is infinitely large. Maybe I can say it is a n tends to infinity. So if you observe, if number of trials are infinitely large, then definitely your success, that is, success goes to 0. Number of trials infinitely large and your success will be 0. Then the third condition is, if this is the case, the average of binomial distribution, maybe I can take a lambda, simple lambda. I can take a lambda. So this is a finite number, right? Expectation of x is a finite number. So expect lambda is a positive real number. You can take positive real number. Okay. So in notation, we can say limit n tends to infinity, binomial distribution, it will be b x n comma p is equal to Poisson distribution. Okay, Poisson distribution. How it will be convert the Poisson distribution? We'll derive this one so that you can remember properly. So first you can take binomial distribution mass function n comma p. How you write? ncx p power x q power n minus x. So can I write this one? ncx p power x q, can I write 1 minus p into n minus x. So now I can write this one, ncx p power x 1 minus p power n minus x. Can I write this one? P by 1 minus p whole power x into 1 minus p whole power n. Okay. So now this I can write n into n minus 1 into n minus 2 into and so on n minus x plus 1 into n minus x factorial upon x factorial into n minus x factorial. So both will be cancelled here. So P, we have written, we have considered that NP is equal to lambda, then P is equal to lambda by n, then Q is equal to 1 minus lambda by n. So this will be, I can write lambda by n whole power x upon 1 minus lambda by n whole power x, this one, into 1 minus lambda by n whole power n. Got it? Now, again I can make it, take n is a common here. That is, let me, I can write 1 minus 1 by n into 1 minus 2 by n into, and so on, into 1 minus x minus 1 by n into n power x, because every term I have taken as a common as n. There are n minus x plus 1 n's are there, that definitely into n. So it is n power x only. Got it? Now this one, it's divides by x factorial. From this, can I write lambda power x into n power minus x by 1 minus lambda by n whole power x into 1 minus lambda by n whole power n. So this will be 1. Now this can be written as, now we can make it as, you can define it 1 minus 1 by n, 1 minus 2 by n, and so on, 1 minus x minus 1 by n into lambda power x into 1 minus lambda by n whole power n upon x factorial. Now, so this is your binomial distribution x and p. Now I can apply limits. Limit n tends to infinity, binomial distribution x n p. Or you can write capital B also, not a problem for this. Okay. So limit n tends to infinity 1 minus 1 by n. Limit n tends to infinity 1 minus 2 by n, and so on. Limit n tends to infinity 1 minus x minus 1 by n into lambda power x into limit n tends to infinity 1 minus lambda by n whole power n upon x factorial. Oh, sorry. X factorial. Here I forgot to write this one. 1 minus lambda by n whole power x also. Okay. Into limit n tends to infinity 1 minus lambda by n whole power x. I think everybody knows as a mathematics experts that you know that in series solutions that limit n tends to infinity 1 minus lambda by n whole power n, and second thing is limit n tends to infinity 1 minus lambda by n power some alpha, where alpha is not in function of x. Alpha is not a function of n. Simple. So this will be e power minus lambda. This will be 1. Okay. So I can write, we know that. Yes, we know that. This will be 1, 1, 1, 1 like that, where you can make it lambda power x. So this is also 1. Only one term will be there. So this is n, and here power is also n. Then I can write it is e power minus lambda by x factorial. This is your Poisson distribution for x ranging from 0, 1, 2, and so on infinity. I can write the P x comma lambda, that is probability of x is equal to x, which is e power minus lambda, lambda power x by x factorial. X ranging from 0 to infinity, 0 otherwise. This is the probability mass function of Poisson distribution. Probability mass function of Poisson distribution. Even this is also valid for this one. Summation x ranging from 0 to infinity, probability of x is equal to x, like that you can write. Okay, this will be e power minus lambda summation x ranging from 0 to infinity, lambda power x by x factorial. What you can write? Lambda power by x factorial, e power minus lambda. This entire thing will be e power lambda. Okay, this will be 1. That is, total probability is equal to 1. So actually, generally we say that Poisson distribution will be applicable in a rare occurrences, such that where the simple example generally we say that number of patients will be joined at the emergency counter in a particular day, or simple number of accidents you met from last 1 month. In last 1 month, how many accidents you met? Of course, we say that the success rate is very low when the number of trails are going to large, very large. That's why we assume that as n tends to infinity, means the number of trails are infinitely large, the definitely success rate is very low actually. See, daily you are coming in the same road and you know that the accident won't happen, but there is a chance to be happen, right? That's reason the success rate is very low. Then that type of situation, Poisson distribution will be applicable. So we can find out the moments of Poisson distribution, that is mu1 dash is, that is expectation of x. You can write summation x ranging from 0 to infinity, x into e power minus lambda, lambda power x by x factorial. Similar way how we have done in the earlier, that you can write this is x ranges from 0 to infinity, x e power minus lambda, lambda power x by x into x minus 1 factorial. Okay, so this can be written as, so xx will be cancelled, and this can be written as lambda into lambda x minus 1 if you write. So this can be lambda can be coming outside, then x ranging from 1 to infinity, e power minus lambda, lambda power x minus 1 by x minus 1 factorial. So this entire thing will be your total probability. Okay, the entire thing will be total probability, or else you can write this one, lambda into e power minus lambda, you can come outside, it will become outside, then it will be 1 plus lambda square by 2 factorial plus lambda cube by 3 factorial plus and so on. Okay, so what is that? This is your e power lambda only. E power minus lambda into e power lambda, it will be 1. So that's why your expectation of x is lambda, that is mean of Poisson distribution is lambda. Then similarly, mu2 dash, expectation of x square, that I can write summation x ranging from 0 to infinity, x into x minus 1 plus x into p of x. I can write this one, summation x is equal to 0 to infinity, x into x minus 1 p of x plus summation x ranging from 0 to infinity x into p of x. So the p of x in nothing but your probability mass function of Poisson distribution, that you can write x ranging from 0 to infinity x into x minus 1 e power minus lambda power x by x factorial plus this, you know that this is lambda, simple, that we have derived here. Okay, so now this one is, what do you get? Summation x ranging from 0 to infinity x into x minus 1 e power minus lambda by x factorial. I can write x into x minus 1 into x minus 2 factorial. Then I can write lambda square into lambda x minus 2 plus it's lambda. So this will be, it's a 2 to infinity you can get. Now lambda square into summation x ranging from 2 to infinity e power minus lambda x minus 2 lambda power x minus 2 by x minus 2 factorial plus lambda. Now after applying this one, lambda square e power lambda minus lambda, you can comment outside. So again this will be, what you can get, summation x ranging from 2 to infinity lambda x power minus 2 by x minus 2 factorial. This entire thing will be 1 plus lambda. So it is, sorry, this is entire thing will be u per lambda you can get. So lambda square plus lambda you can get for your expectation of x square. Okay, so now variance is equal to mu2 dash minus mu1 dash square lambda square plus lambda minus lambda square. Again your variance all will come is same as expectation. So in Poisson distribution, you can say in Poisson distribution generally expectation of x is equal to variance of x. Mean and variance are equal in Poisson distribution, like that you can write. Okay, like you can write mean and variance are same for Poisson distribution. If let be, మనకి ఎలా అంటే ఒక క్వశ్చన్ లోన మీన్ ఆఫ్ పాయిజన్ డిస్ట్రిబ్యూషన్ అని రాసిన తర్వాత అసలు వేరియన్స్ మెన్షన్ చేయకపోతే మనం ఇన్బిల్డ్ గా అనుకోవాలన్నమాట. సో మీన్ వేరియన్స్ సేమ్ కాబట్టి వాట్ ఎవర్ ద మీన్ అంటే ఎంత మీన్ ఇచ్చింటారో వేరియన్స్ కూడా అంతే ఉంటుందని మీనింగ్ అక్కడ. సో we can derive the moment generating function of Poisson distribution. So mx of t summation x ranging from 0 to infinity e power tx e power lambda power x by x factorial. Okay, this can be written as summation x ranging from 0 to infinity e power, sorry, it's minus lambda, e power minus lambda. So this can I write lambda into e power t whole power x by x factorial. Okay, so now e power minus lambda I can get it outside. So the expansion of this one, that expansion, that is x ranging from 0 to infinity lambda e power t whole power x by x factorial. How you can get the expansion for this? 1 plus lambda e power t plus lambda e power t whole square by 2 factorial plus and so on. Okay. So this will be e power minus lambda. This entire thing will be e power lambda e power t. So instead of x, you got lambda e power t. This entire expansion is your e power x, if you say 1 plus x square by 2 factorial plus x cube by 3 factorial, like that. So this I can write e power lambda into e power t minus 1. This is your moment generating function of Poisson distribution. Similarly, simple you can write. How you can write the characteristics function of Poisson distribution? Simple. E power lambda, just e power lambda into e power it minus 1. That's it. Okay. So like that you can derive your moment generating function and characteristics function of Poisson distribution. Now coming to negative binomial distribution. Why it called negative and all we can discuss. Negative binomial distribution. Actually, in binomial distribution, mean is always greater than variance. Okay. In Poisson distribution, mean is equal to variance. Sometimes, for example, if you have a number of deaths by some insects, or with number of deaths of insects, here mean will be less than your variance. Okay. So that type of situation, negative binomial distribution will be helpful. So now here, same, we can repeat it the n number of Bernoulli trials. So n Bernoulli trials. And the trials are independent. Trials are independent. And as usual, P remains constant. P remains constant. Means the success remain constant in even negative binomial distribution. Now, we'll write the function let f of x r comma t. Denote that probability that there are x failures preceding n minus x, x plus r successes. Preceding the rth successes in x plus r trails. There are x plus r trails. You are repeating your trail till the success will be reached. You are repeating the number of trails till success will be reached. So if the last trail must be success, definitely, because once you success you reach, then you stop your procedure generally. Okay. In the x plus r, success is 1. That is, in x plus r trails, how many trails are there in x plus r trails? Success you got, the remaining x plus r minus 1 failures. Okay. R maybe, it's not, you can say it's x plus r minus 1 trials, you can say. If x plus r trails are there, one you got p, that is success. The remaining how many trails will be there? X plus r minus 1. In remaining x plus r minus 1 trails, you must have r minus 1 successes. In the remaining, x plus r minus 1 trials, we must have r minus 1 failures, because we have rth success. So r times, in rth time we got a success. So definitely r minus 1 we got the failures. So drawing the success from x plus r minus 1, then I can say it is x plus r minus 1 c r minus 1 p power r minus 1 into q power x for this one, into final one is p. So this I can write x plus r minus 1 c r minus 1 p power r into q power x. Okay. So the probability mass function of negative binomial distribution is, so let a random variable x follows a negative binomial distribution. It's a probability mass function is given by like that. You can write probability of x is equal to x, that is x plus r minus 1 c r minus 1 p power r into q power x, and x range from 0, 1, 2 and so on, 0 otherwise. Okay. Even you can simplify this one, why it will be called as a negative binomial distribution. That you know that x plus r minus 1 c r minus 1, can I write this is x plus r minus 1 cx, as per this one ncr, I can write nc n minus r also, based on that. So this can be written as x plus r minus 1 x plus r minus 2 into and so on r plus 1 r minus 1 factorial upon x factorial into x plus r minus 1 minus x factorial. So x is, you can get it is your r minus 1 factorial. So this can be written as x plus r minus 1 x plus r minus 2 and so on r plus 1 r upon x factorial. So again I can simplify this one, minus 1 whole power x, this I can write minus r minus 1 and so on, minus r minus x plus 2 minus r minus x plus 1 upon x factorial. So can I write this one? Minus 1 whole power x minus r cx minus r cx. Okay. Now your probability mass function of negative binomial will be minus r cx p power r minus 1 whole power x, and q power x will be minus q whole power x for x. Zero and so on. Actually, which is the x plus 1th term in the expansion of, this is the x plus 1th term in the expansion of p power r into 1 minus q whole power minus r. A binomial expansion with a negative sign. So that's why this will be called as a negative binomial distribution. Even total probability is equal to 1 here also. You can make that summation x is equal to 0 to infinity p of x. That is, you can write p power r outside. Summation x ranging from 0 to infinity minus r cx minus q whole power x. So this will be p power r. This entire thing, how I can write? 1 minus q whole power minus r. So 1 minus q is p power r, p power minus r. It will be 1. So for calculating the what do you say, moments of negative binomial distribution, we'll convert this. Like if you take small p is equal to 1 by capital Q and small q is equal to capital B by, so capital P by capital Q, so that Q minus P is equal to 1. Q minus P is equal to 1, which means small p plus small q is equal to 1. Even from this also you can write Q is 1 by Q minus P by Q. So 1 minus P by Q. Here you can write it's a Q by Q. It will be 1. So based on that only I have written this. Now mass function is minus RCX Q power minus R minus P by Q whole power X. Actually, from this, where it is, yeah. From this, if R is equal to 1, your P of X is equal to simple Q power X into P. Or else you can say it is from this one. X plus R minus 1C, R minus 1, P power X into Q. Sorry, P power R into Q power X. If R is equal to 1, this will be converted to Q power X into P. Actually, this is your geometric distribution. So in notations, we write at R is equal to 1, the negative binomial distribution tends to geometric distribution. Negative binomial distribution tends to geometric distribution. So from this we can derive using binomial distribution. Sorry, moment generating function of this negative binomial distribution will derive the moments So moment generating function of negative binomial distribution. Moment generating function of negative binomial distribution, that is mx of t, expectation of e power tx. So this I can write summation x range from 0 to infinity minus r cx q power minus r minus e power tx and p by q x, right? I can add minus p e power t by q whole power x. So this is like this can be written as q minus p into e power t whole power minus r. This is the expansion of this one. This is your moment generating function of negative binomial distribution. So first one is, as per the definition we have written the moment generating function, because it's you can draw the moments from the moment generating function, because moment generating function generates the moments, right? So first moment will be derivative with respect to t of your moment generating function. At t is equal to 0, you can get the first one. So this one minus r into q minus p e power t whole power minus r minus 1 into minus p e power t at t is equal to 0. What do you get? R into capital P. So this is your mean of negative binomial distribution. Mean of negative binomial distribution is R into capital P. And then similarly, mu2 dash, that is second derivative with respect to t of your moment generating function at t is equal to 0. So this I can write directly. I can write from this one. So this is what? R into p e power t q minus e power t power minus r minus 1. So this I can write r into p e power t into q minus p e power t whole power minus r minus 1 plus minus r minus 1 r into p e power t q minus p e power t whole power minus r minus 2 into minus p e power t at t is equal to 0. So this I can get r into capital P plus r into r plus 1 p square you can get. I think here is a minus, right? Now this is your mu2 dash. So mu2 is equal to mu2 dash minus mu1 dash square. So that will be r into r plus 1 p square plus rp minus r square p square. So this will be r capital P capital Q. This is your variance of x of negative binomial distribution. As q greater than 1, that is rp is less than rp q. Is that mean is less than variance. But in binomial distribution, np is greater than npq. Now it is less than you can get. Even Poisson distribution is a limiting case of negative binomial distribution. By taking r tends to infinity, definitely your capital P tends to 0, so that r into capital P is equal to some lambda. So as we have done in earlier, similar way if you done, you can get this, what do you say, limit r tends to infinity, negative binomial distribution will be converted into e power minus lambda, lambda power x by x factor you can get. Okay. You can solve one problem, I can give it here, and then we'll stop today's class. The problem is, an item produced in large numbers. The machine is known to produce 5% defectives. A quality control inspector, a quality control inspector is going to examine the items by taking them at random. So now the question is, what is the probability that at least 4 items are to be examined in order to get 2 defects or 2 defectives? What is the probability? Here, solution is, if 2 defects are to be obtained, is that 2 defects are to be obtained, so definitely your trials are 2 or more. Exactly 2 cannot be obtained. Your trials are 2 or more, and the success is P is equal to 0.05. P is 0.05 for every trial. So it is a negative binomial distribution that you have to find out probability at x is equal to 4 plus probability at x is equal to 5 plus and so on. Because minimum 4 items should be examined. Minimum 4 means that 4 or 5 or 6 or maybe you don't know how many. But you should get at least 2 defects. So here you can write like summation x ranging from 4 to infinity, x minus 1 C2 minus 1 P power R into Q power x minus R. So these can I write 1 minus summation x ranging from 2 to 3 x minus 1 2 minus 1 square minus 5 x minus 2. So that is 1 minus 0.05 whole square plus 2 into 0.05 whole square into 0.95. So that is 0.995. This is your answer. So tomorrow we'll discuss about geometric distribution and hypergeometric distribution, some properties of geometric distribution also. Okay. So any doubt today regarding today's class?
No, sir.
Okay. You can
కొంచెం
post in the
తెలుగు
chat.
టర్మినాలజీ కూడా యూజ్ చేయండి సార్.
Okay. Okay, ఇంకా ఏమైనా doubts? So shall we stop today's class?